Hello everyone, my name is Derek, and today I'm going to talk about our work on surface multigrid via intrinsic prolongation. And this is a joint work with Aris, Mariela, and Alec. So in this work, we present a new multigrid method for solving linear systems defined on surface triangle meshes. The reason we work on linear solvers is because they are the fundamental building block for many applications, and here we just list a few of them. And to understand how these methods use linear solvers, let's take a look at this mean curvature flow as an example. So this algorithm starts by loading a geometry, assemble the system matrix A, build the right-hand side B, and then solve the linear system to get a deformed shape. And typically, a single iteration is not enough, so we'll go through this process of rebuilding and solving different linear systems multiple times until we converge. And when we implement that algorithm, the go-to linear solver we use nowadays is perhaps the Cholesky factorization. And this is actually a very ideal solver when you work on low resolution meshes with a couple thousand vertices, because you can efficiently obtain a solution in a matter of seconds. However, Cholesky solver scales poorly when you work on high resolution models. For example, if your input mesh is this highly detailed fossil scan with millions of vertices, then you'll need to wait for a few minutes in order to run a single iteration. So the goal of this work is to develop a more scalable linear solver to bring down this line. And our solution is to use the multigrid methods. But before introducing our solution, you may wonder why we consider multigrid solvers instead of other linear solvers. And one reason is because multigrid solvers are perhaps the most scalable solver in scientific computing. And to get a feeling of how scalable it is, here are two examples that use multigrid methods to solve extremely large-scale systems. And specifically, the scale they consider here are systems with 3 billion vertices and 5 billion vertices, respectively. And another reason we choose multigrid methods is due to the precomputation. So let's come back to this example algorithm of mean curvature flow. If we want to use the Cholesky solver, we have to do the precomputation after we construct the system matrix A. And because we are getting a different system matrix at every iteration, so we'll have to keep redoing this expensive precomputation at every iteration. And as a result, it will make this algorithm slow when you work on high resolution models. In contrast, if we are using geometric multigrid, the precomputation only depends on the geometry. So even if you update the system matrix at every iteration, you can still reuse the same precomputation and efficiently run this algorithm. So because of this reason, using Cholesky will make this algorithm scales poorly. But if we switch to multigrid, you can achieve a linear time complexity even with a CPU implementation. But you may wonder that if multigrid is so appealing, why they are not ubiquitous in geometry processing? The main reason is because most multigrid methods are limited to regular grids, such as images or voxels. And there are attempts trying to overcome this limitation. They focus on generalizing multigrid methods to Euclidean meshes, such as triangle meshes in 2D or tetrahedral meshes in 3D. However, if you search around multigrid solvers for surface meshes embedded in 3D, to the best of my knowledge, there's only a single paper that addressed this question. And it is quite disappointing that surface meshes are perhaps the most widely used representation in graphics, but we do not have a good multigrid solver for that. So for people who are familiar with multigrid solvers, you may wonder, why don't we use something called the algebraic multigrid methods? So in a nutshell, algebraic multigrid perceives the geometry as a graph. And because of this treatment, we lose a lot of important geometric information for us to define an efficient multigrid method. And in our experiment, algebraic method converge slower compared to our multigrid method, which takes geometric information into consideration. And another reason is because the precomputation of algebraic multigrid also depends on the system matrix A, so it also requires to do precomputation at every iteration. So hope right now I have convinced you that Geometric Multigrid is a good scalable solver, but we have to come up with a way to define it on surface meshes. But before that, let's have a quick refresher on multigrid methods. So multigrid method is an iterative method for solving linear system AX equals to B. And this is a hierarchical solver, which requires us to define our domain with different resolutions. And given an initial solution xi, we will go through the entire hierarchy called the V cycle and get the updated solution, which is closer to the true solution. And typically, multigrid will consist of several levels, but here we just show two for simplicity. So now let's talk about the solver step by step. First, we will initialize the solution xi, represented using the colors. And because this initial solution could be very bad, so if we visualize the residual as the height here, you'll see that there's a big error. And the first step is the relaxation. And people typically use basic iterative methods such as Jacobi or Gauss-Seidel to improve the solution. So these basic iterative methods are actually quite effective in removing high frequency errors. So you can see that after a few relaxation steps, what we left here is just the residual with low frequencies. And the next step is the restriction, which basically downsamples the residual from the fine grid to the coarse grid. Then we will solve the residual system to get an update UC. And usually we will use a direct solver here because when we reach the coarsest level in the multigrid hierarchy, we usually don't have a lot of degrees of freedom, so we can solve it efficiently. So after we solve the update UC, the next step is to interpolate the update from the coarse grid to the fine grid. And this process is usually called the prolongation in the multigrid literature. And then we can combine the update U with the initial guess xi to get our new solution x spline. By incorporating the updates from the coarse grid, we can already reduce the residual a lot, as you can see here. And finally, we will also do another few relaxation steps to further remove the high frequency errors from the previous step. So that leaves us the update solution xi plus 1 for the next iteration, and multigrid method will do the speed cycle for multiple iterations until we converge. So among these procedures, how to define the hierarchy, prolongation, restriction, and the quiescent linear system are the key to determining the convergence rate of the solver. And a widely used formulation called the Galerkin Multigrid defines the prolongation using a linear operator P, which is a tall matrix that interpolates signals from the coarse to fine. And the restriction is defined as the transpose of the prolongation P. And to define the quiescent linear system, Galerkin Multigrid used the prolongation P to sandwich the system matrix A. And you will notice that every component here is defined based on P. So in other words, prolongation is all you need in order to implement a Galerkin multigrid method. So after knowing the importance of prolongation, it is easy to understand why people prefer to work on regular grids, because you can easily use, for example, bilinear interpolation to construct the prolongation operator. And if you're on a Euclidean mesh such as this 2D triangle mesh, defining prolongation is also not so difficult. For example, you can simply use the barycentric coordinate to define it. But the only difference is that you'll need to have extra care on the boundary. But how about prolongation on curved surfaces embedded in 3D? A naive approach is to use a closest point projection, but this will lead to terrible failure cases. So take this wine glass as an example. If we cut it and look at its cross section, where we use the gray dotted line to represent the original mesh, and the black solid line to represent the quiescent mesh. And let's say you want to do an interpolation for this point in gray, using its closest point on the quiescent mesh showing black. But this is completely wrong, because you will be using the solutions in the inner part of this wine glass representing green to determine the solution on the outer part highlighted in red, and this will make your multigrid solver fail completely. So for example, here's the result of heat diffusion where the heat source is placed inside the wine glass. And if you didn't do this prolongation properly, you'll see an incorrect behavior where the heat does not diffuse along the surface. So here we will talk about how to obtain a better prolongation leveraging the intrinsic geometry. So given the high resolution shape, we can construct the multigrid hierarchy using a standard mesh decimation. And the key idea to obtain the prolongation operator is to successively compute the parameterization on the fly during the decimation. So let's first consider a mesh on the left and its simplified version on the right. And the simplified version is computed from a sequence of edge collapses. And the main idea is that instead of computing this map F directly between level 0 and level L, we can consider it as a composition of many small maps. And if we can figure out how to compute the mapping between a single edge collapse, then we can easily recover the entire map using composition. So let's zoom into the case of single edge collapse. Given a point with its barycentric coordinates, how can you obtain the corresponding point on the patch before the collapse? It is pretty straightforward. We can simply copy and paste this barycentric information and obtain the corresponding point because the mesh at this region does not change. But how about a point here? If I hand you a point here, it is unclear what will be the corresponding point of this one because the one ring neighbors highlighted in red has a different connectivity after the collapse. So we cannot simply copy and paste the barycentric coordinates. So let's further zoom in to focus on this edge one ring. And the key idea here is to leverage the fact that the boundary curves remains the same after the collapse, so we can utilize this property to simultaneously flatten both patches into 2D and ensure the 2D boundary curves also remains the same. This can be achieved by solving a joint parameterization problem, where we want to minimize the summation of the distortion energy, like the conformal energy, subject to the constraint that boundary UVs needs to be the same. And this boils down to solving a very small linear system, and we can also generalize this collapsing edge along the open boundary of the mesh. So after we have this joint parameterization, given a point, we can use the barycentric coordinate to figure out its location in 2D. Then we can recompute the barycentric coordinate using the triangulation before the collapse in order to figure out its corresponding 3D location. And that's how we obtain the mapping between a single edge collapse. Then we can get a full map using composition. So as a result, for each vertex V, we can use this map to query its corresponding point on the coarser mesh, and vice versa. And because this map is bijective, the corresponding point FV could locate in the middle of a triangle. Then, we can easily use the barycentric coordinate to define the prolongation operator. And this way of computing the map is applicable to different manifold triangle meshes with or without boundaries. So here we just visualize the map by plotting the coarse triangulations on top of the high resolution meshes with colored triangles. So now we have everything we need. Just a brief recap, we compute the multigrid hierarchy using standard decimation. And during the decimation, we compute the parameterization on the fly. And this allows us to define the prolongation using simply the barycentric coordinates. And here we show that the multigrid solver defined using our prolongation converges faster than the only surface multigrid method that is available. And you can also find more comparisons in the paper. So now let's take a look at some results. So we first look at the fundamental problem, data smoothing. The entire algorithm boils down to solving a single linear system. And both the left-hand side and the right-hand side depends on user's specified smoothness parameter alpha. And here we can see that by manipulating different smoothness parameters, we can obtain different smoothing results. And usually the optimal alpha is unknown. So the user have to play with this alpha in order to obtain good results. But because Cholesky requires to do prefactorization whenever a user changes the parameter alpha, so we have to wait for a couple seconds in order to see the update. In contrast, our multigrid method only needs 0.3 seconds. And to get a feeling of how big the difference is, let's do a live demo. So here is a live demo of our data smoothing experiment. So in the middle, you're seeing our input step, the dragon, and we are seeing the noisy input function as the colors on top of the surface. And in this user interface, our first row has an option to switch back and forth between our multigrid solver and the Cholesky solver. And right now, we're using the Cholesky solver. And the second row is the alpha parameter, which controls the smoothness of the output function. Basically, you can drag back and forth between the different alphas and get different smoothing results. So let's start with the Cholesky solver. So now what I will do is that I will drag this alpha parameter and let's see how much time we need to wait for the Cholesky solver. So now I will drag and we're waiting. And because Cholesky requires to do precomputation, so usually it will take a few seconds to see the result, as you can see right now. And let's do that again. If I drag and wait, and like after a few seconds, we can see the update of the result, which is okay, but not really satisfying. But let's take a look at our multigrid solver. So now we switch to our multigrid solvers. And because multigrid solver is like orders of magnitude faster, so we can now like drag back and forth between different alphas. I can see that the ISO line on the surface change interactively whenever we drag this alpha parameter. So we can make it very small to see a noisy function. We can also make it big to see a very small function. So in addition to the demo, here's a more complete picture of the runtime. So basically, Cholesky is orders of magnitude slower than the CPU implementation of our multigrid method. Another application is the balloon simulation. Here we simulate this bunny using the Cholesky solver, which will take a while to run just a single iteration. But if we replace the Cholesky solver with our multigrid method, we can run this algorithm with 28 times speed up. And for other applications such as the polycube deformation, fluid simulation, and the mean curvature flow, the stories are the same. We can make all of them faster and the amount of speed up depending on the resolution of the input mesh. If you're using a high resolution model, the speed up will be greater. And to conclude, in this work, we present a geometric multigrid solver for curved surfaces. And our method is a drop-in replacement of the Cholesky factorization. And our method can achieve an approximate solution very quickly, but it will take much longer if you want to get a highly accurate solution. So it will be interesting to use our multigrid method as a preconditioner to other iterative methods such as a conjugate gradient, because in practice, this helps improving the convergence. Another limitation is that our method is also sensitive to mesh quality compared to the Cholesky solver. So it will be interesting to see whether we can combine with other remeshing algorithms such as the intrinsic refinement to make this solver agnostic to mesh quality. So lastly, I would like to thank all the funding agencies and thank you all for your time.